Hello and welcome to this video which accompanies our work, Risk-Bounded Nonlinear Robot Motion Planning with Integrated Perception and Control. In this work, we propose a risk-based two-level autonomy stack. The high-level module is our novel sampling-based motion planner, NRB RRT star. It samples the free space and builds a tree from the initial state to the goal region while performing a distributionally robust collision avoidance check. The returned reference trajectory is passed down to the low-level module, which tracks it using nonlinear model predictive control. Ideally, the high-level motion planner would take the initial state and goal region as inputs and solve an optimization problem to find an output and input history-dependent control policy. The control problem minimizes a stage cost and a terminal cost subject to the nonlinear dynamics with process noise, a noisy nonlinear output model, initial state uncertainty described by a moment-based ambiguity set, the distribution of noises being known with their first two moments, input constraints, and a DR risk constraint requiring the state to remain in the free space. However, the DR risk constraint is infinite dimensional and the free space is generally non-convex, making the problem hard to solve. Instead, our solution solves the problem using sampling-based motion planning with two key modifications. One, we use an output feedback-based NMPC steering law with an unscented Kalman filter for state estimation. And two, we apply the distributionally robust collision avoidance check to trajectories between sampled states. The collision avoidance check requires all trajectory waypoints to satisfy a DR collision check, and it requires successive waypoints to be in the same half-space so that interpolations between them are collision-free. Our NRB RRT star algorithm then grows the tree by sampling a node in the free space using a nonlinear steering law to connect to the sampled nodes, performing a DR collision check to ensure that the trajectory is safe, and finally performing the RRT star routines of connecting the node via a minimum cost path and rewiring the tree. This results in a safer and more conservative solution that connects the initial state to the goal location. The resulting reference trajectory is passed down to the low-level trajectory tracking module. At each step, the controller considers part of the reference trajectory according to a look-ahead horizon and plans an optimal trajectory from the current measured state to a desired state at the end of the horizon. The controller minimizes deviations from the reference trajectory and control effort, subject to the nonlinear dynamics and output model with the realized process and sensor noise, the known distributions of the process and measurement noise, the moment-based ambiguity set that the initial state belongs to, and the input constraints. The first control in this sequence is applied to the system, then the outputs are measured and the process is repeated in a model predictive control fashion. In this video, we use Carla, a high-fidelity simulator, to demonstrate the effectiveness of our algorithm. The NRB RRT star tree is overlaid in red, and the reference is highlighted in yellow. The realized trajectory is depicted in blue. The vehicle makes its way around the parked car using the reference trajectory. The eco-vehicle avoids collisions despite the measurement noise, process noise, and unmodeled dynamics thanks to the safe planned trajectory. We also perform a simulation of an overtaking maneuver. The eagle vehicle starts off behind the dynamic obstacle, then it moves left, overtakes the obstacle, then merges back into its original lane. For more details, please check out our paper, Risk-Bounded Nonlinear Robot Motion Planning with Integrated Perception and Control. Thank you for your time and attention.